computer. Welcome to Chemistry 2330. I'm Dr. David Irvin. I have a question in the group chat about a group me. If somebody would like to create a group me and go ahead and put that on Canvas, that'd be great, because I don't want to actually monitor or do anything in the group me. If you could set one up and invite everybody, or set one up and put the link in the chat there, that'd be great, so that you can keep on tabs of when things are going, and is he wearing the same shirt again? Whatever you want to say on the group me. And yes, I have 3 of these, so it looks like I'm wearing the same shirt all the time. But it's great for continuity in my videos. So, okay, so we're right here at 11 o'clock. So I'm going to go ahead. I've already started recording. Sorry about the slight delay in posting this video yesterday. I had run up to the lab to do something and I forgot to do it, but I'll try to post it even more. The textbook is not on Top Hat. The textbook is a physical copy of the Brown and Poon, the green book. I have a copy around here somewhere. It's actually really, I think it's really perfect level for this class. So it's a great thing. So last time, before I start, does anybody have any questions up to now about administration, when our homework's due, or anything like that? I think the button.
I did.
Go ahead.
I don't know if I missed this or not, but I know in the past we used to have mandatory SI sessions. I didn't know if that was still being continued.
This class does not have an SI session. Okay, the SI sessions are for other classes and other chemistry classes. This particular one, because it's unique to the health sciences majors, etc., and wildlife biology majors, we do not have one. But I will have office hours, and we can do, a mini SI session in the office hours. Okay, so I thought that presenting on Top Hat was a little clunky, so I wanted to try to present it the way I've done it in past semesters, using my iPad, and I can actually draw a little bit more on that. So I'm going to try to present our set of slides here that way, and then we can compare and contrast and see if people like that more. Couldn't find an attendance policy on the syllabus. We do not have an attendance policy due to the relaxed COVID-19 approach at Texas State. Our attendance policy basically does not exist, but I encourage you to attend live so you can ask questions. And if you do get sick, stay home and catch up with the videos. So that's our plan for this semester. Okay, and note there is a group me. Somebody started a group me in the chat room. So if you could go ahead and do that. I can copy that and put it into I'll put it in Canvas so that you can have it under discussions or announcements. It'll be under announcements. New announcements and paste. Oh. And if I can just copy and, all right, there we go. Paste. So there is an announcement with the new group me on there. So go ahead and log in as you see fit. Okay, yeah, and thank you very much for setting that up. All right, I'm going to try to share my iPad and see if we can't get a nice, more annotated lecture there. Okay, okay. I can trust this computer. Why are we doing that? Okay. Stop share. All right, that's not working today. What is going on? Sorry, this is weird. I don't know why it's not letting me do that. Stop share. IG. Sorry, it worked just 5 minutes ago. What is wrong here? Is that it? Yes. There we go. There we go. Can everybody see that screen now? Yeah. All right. Great. All right. Thank you. Oh, not that. I want to move this. Okay. So I'm going to go ahead and clear up my screen here and move all your shining faces on this screen over here. So where we left off last time was we were talking about Lewis structures and how to predict the bond angles from these. Remember, our Lewis structures, we want to see that the bonds are 2 electrons and any lone pairs, and those electronic regions control the shape. And if there is a bond there, that controls the shape of the molecule. The number of electronic regions controls the electronic state. So for example, we could have a compound like this that once we drew the Lewis dot structure, we would start with having an O with an H because our carbon's going to be in the middle because it's the least electronegative atom other than hydrogen. And we'll find out that we had to put our lone pairs in here, but then we had to share another lone pair to give it to our system here. So just from that configuration, there's that's telling us we have 1, 2, 3 bonds to carbon plus a double bond, meaning that this right here is going to be trigonal planar. So there seems to be a little delay here, but it's working. So that's how you use the Lewis dot structures and the electronic regions to help control those bond angles. So let's take that and do it a little bit more. Let's predict where these angles will be here. So this compound right here is called benzene. We're going to talk about it in chapter 9, and it's got some really cool stuff. But using what we've already learned just in chapter 1, we can predict the angles in all of these things. So just like before, we saw our Lewis dot structure, and our Lewis dot structure is complete here. There are no lone pairs. So we can actually predict from this because we have 1, 2, 3 electronic regions. We can say that this is going to give us 120 degrees on each of those angles, both the hydrogen carbon carbon and the carbon 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 bond. And why are we lagging? Okay, let me do one more different share then. Share, screen mirroring. This is frustrating because it worked just 5 minutes ago. Okay, we're gonna have to do it the other way then. I'm sorry. I'll figure this out this afternoon. Okay. Oh, that's true. Okay, I apologize for that. Technology is great until it's not. Okay. Almost there. Okay. So this is where we were, and we were saying that just from looking at those electronic regions, we can tell what the angle will be for each of these bonds. So between the hydrogen, the carbon, and the carbon, it's going to be 120 degrees. Between each of the carbons, it's going to be 120 degrees because we have those three equal sections there. So that means we can actually predict that this molecule is going to be very flat and very rigid. And we'll go through that in more detail in chapter 9. Okay, so now that we have a way of figuring out what the molecule looks like by the Lewis dot structure, and by making sure when we do our Lewis dot structures, we put in where all of the electrons are, including those lone pairs, that gives us an idea about the shape of the molecule. But that doesn't tell us necessarily about whether or not the molecule is polar or not. Okay, so let's go back and talk about those polar bonds. When we had polar bonds, that was defined as having a bond between two atoms that was greater than 0.5 difference in electronegativity, but less than 2. So all of those bonds, there's like 1.5 difference in electronegativity where we can create these polar bonds. Okay, so what does this kind of really mean? What this means is that in the case of this polar bond here, carbon is less electronegative than oxygen, okay? Which means it doesn't want electrons as much as oxygen does. So what oxygen is going to do is it's going to pull some of that electron density toward it. It's not breaking the bond, it's just polarizing the bond. More of the electron density is on the oxygen. And because this carbon particularly is bonded to 2, this one's going to pull it in this direction. Okay, so if that oxygen is pulling some of the electron density to one direction, we call that a dipole. Okay, a dipole is something with 2 poles on it. We have a positive side and a negative side of that vector or that direction. Okay, so that dipole means that we have a net negative side of the bond and a net positive side of the bond. Okay, so when we think about whether a molecule is polar or nonpolar, we actually have to add up all of the polar bonds and see which direction they point. Okay, so in this case here, we have one bond that is pulling, to the right here, and it has a carbon-oxygen double bond. So that's the strength of that dipole, is that whatever that difference in electronegativity is. The next one we have is we have another one going in the opposite direction to the left, okay? Now, because it's the exact same atoms and the exact same bond type of having 2 bonds there, the double bond, that means both of these dipoles are equal in strength, okay? So if they are equal in strength, we can actually sum them up to see if this molecule is polar or not. As it turns out, because they're equal strength, but they're in exact opposite directions. So that means the 2 vectors cancel each other out, making this a non-polar molecule. Even though we have 2 polar bonds in this molecule, the fact that they are equal and opposite each other cancels them out. Does this happen in all molecules? Absolutely not. And so we have to pay attention to which bonds are polar, which direction the dipole goes into, and then look at the sum of where they're all pointing. So let's look at one of those, and let's look at something like water, okay? We know water is a polar molecule because we were taught that in organic and in Gen Chem. So let's remember why that's true. So oxygen is more electronegative than the hydrogens here. So oxygen is going to polarize that bond, giving the hydrogen the positive side, partially positive side of that bond, and the oxygen the partially negative side of that bond. Okay, so this particular vector then is in this direction where it's negative on this side and positive on this side. Okay, now let's look at the other bond. The other bond is going in this direction here. Okay, now These are equal in strength, but they are not equal and opposite in direction. So what we have is each of these vectors actually has two components. One is up and one is to the side. One is up and one is to the side. The ones to the side actually cancel each other out, giving us a net dipole in this up and down direction. Okay, so if we're thinking about this, the two parts that tilting each other out, we actually are going to equal and opposite those, but we have two vectors pointing up. So we have a net polar molecule. Look at each of the bonds first, then look at the molecule as a whole. Do they add together, or do they subtract, or do they cancel each other out? Okay, now, does this also apply to things with lone pairs? And the answer is yes, because we have lone pairs here on this oxygen. So it applies to things that have lone pairs or don't have lone pairs. But the net vector tells us something about whether the molecule as a whole is polar. Okay. So let's look at a different geometry here. So just like in the case of the oxygen before, electronically it's tetrahedral. It has 4 electronic zones, but it only has 2 bonds in water. Here we have 3 bonds, okay? And we have the same thing that happens. Nitrogen is more electronegative than hydrogen, and therefore we have each of the hydrogens is going to provide a vector in this direction. But because all these the vectors are going toward the same nitrogen, all of the ones to the side cancel out, and we just have the net one going up and down. So our net dipole is actually going to be in this direction. And in this case, the dipole actually aligns with the lone pair. In the other case, the dipole was in between the 2 lone pairs. So don't think of the lone pair as giving you polarity. Think of the vectors of the polar bonds. Okay, all right. Sorry, my chat was uncovered a little bit. There we go. All right.
I have a question.
Yes.
Do, do lone pairs provide like a stronger attraction?
No, lone pairs can be used in certain bonding types, and we'll talk about that. That's specifically hydrogen bonding. But in the case of polarity, all we're looking at is the polar bonds. Look at each polar bond and the net result of where they all point. That gives us polarity. Okay? All right. So polar bonds can look a bunch of different ways, because you can have a wide variety of things that you can do. So let's look at this one right here. Here we took methane, which is carbon with 4 hydrogens on it, and replaced one of those hydrogens with chlorine. That changes the dynamic, okay? Before we added that chlorine, carbon was the most electronegative atom and pulled electron density in from each of the hydrogens, okay? But now chlorine is the most electronegative atom, okay? So these are still slightly polar bonds here and all going in that direction, but the major component here is now the draw of the chlorine, because those hydrogens cancel out the side portions, and so all 3 hydrogens are additive up, and the chlorine carbon bond also has a net dipole in the up direction. So that means chloromethane, just replacing one hydrogen with chlorine, makes it a polar molecule. Now, do they have to be tetrahedral in molecular shape? No. All we're looking for is the net result of all of our polar bonds. Again, we have these 2 components coming in together where our hydrogens are, but we also have oxygen being our most electronegative atom, and therefore this bond is also polar in that direction, giving us a net dipole along that carbon-oxygen double bond. Now, that's with single bonds and double bonds. Can we do it with a triple bond? Well, in this particular case, we have the 2 carbons have a non-polar bond in between them because they both have the same electronegativity. The hydrogen here is slightly less electronegative, so the carbon is going to pull in a little bit of electron density this direction. And look what we have now. We have equal and opposite again, making acetylene a non-polar molecule. Okay. All right, so does that make sense? You add up all the directions of the polar bonds to give you polarity of the molecule. Okay, so and this was actually brought up in the last class about, is there only one way to draw a Lewis dot structure? And sometimes in the case of places, especially when you have an ion and you have the same atom sprinkled around, it might be possible to draw more than one Lewis dot structure that accurately portrays the material. And the reason for this is that, is there really a difference between each of these oxygens? So let's look at this one right here, the first one right here. And unless you actually put a 1, a 2, and a 3 on here, there's no difference in any of these oxygens. All those oxygens should be exactly the same because they're each an atom of oxygen. So there's no particular reason why they need to be in this particular format. Okay, so why can't we take these electrons, move them down here, and move these electrons up here and have the negative charge here? There is no reason. That's an equivalent, chemically equivalent structure. And when we do that, we actually end up making it look like this structure here. Okay. So are they different at all? No, they're not. And so we have two possible structures that show the same thing. Well, it turns out that we can also do that with this other oxygen here to give us the double bond can be on any of the 3 oxygens in any one Lewis dot structure. Okay, so if this is possible and they all seem to be identical in electronegativity and charge, we tend to call this, well, this is what we call resonance structure. If you can draw more than one Lewis dot structure that's valid for a species, they tend to have resonance structure. All right, I have a question. Do you have to draw the correct angles in the Lewis dot structures, or can you draw all the angles at 90 degrees? When you're drawing the Lewis dot structure, you can just draw it such that you get it on the paper, but you need to remember that you're representing a 3-dimensional object. So just remember it is a 3-dimensional object when you start putting vectors in. So that's answering a question. Okay, so resonance is valuable to us because it tells us something about the molecule in particular. Number one, in this particular case, it tells us that all of those oxygens are the same, and that means that we're spreading those 2 negative charges out over 3 whole atoms. Okay, if we're spreading 2 charges out over 3 whole atoms, that's going to give us some stability. Okay. So this kind of goes back a little ways and saying that, hey, we can draw a bunch of different Lewis structures for the same combination of elements. Okay. And if we can draw a number of valid Lewis structures for the same grouping of elements, maybe in reality, when it's floating around in the solution, it actually does this on its own. Okay. So we have to make sure we follow a couple rules to make sure that we have our resonance structures and that we keep them valid. And we do this by looking at each one independently and then just moving 2 electrons around the system to see if we can create a new valid structure. Okay. Okay. So, and when we do this, the one Lewis dot structure we started with is a contributing structure. The next Lewis dot structure that is valid is also a contributing structure. So the bare minimum you can have is 2 structures that look about the same, except they have the charge on a different atom. But you can have 3, 4, 5, depending on how many possible atoms you could spread that charge out over. Okay. So let's demonstrate that a little bit. And we already looked at this one a little bit, and this one was carbonate, okay? And we were able to draw 3 contributing structures to this carbonate. And because we had 3 different oxygens that could be double bonded to the carbon center, okay? So to make sure we're doing it correctly, we need to make sure we're moving 2 electrons at a time when we do it. And typically when we draw electrons moving, we draw a curved line with 2 prongs on the end. The 2 prongs mean 2 electrons. So that's kind of important. When we do that, that puts the lone pair up on this oxygen, and we have to make sure that our center atom still has 8 electrons. So to do that, we're going to take 2 electrons from a neighboring oxygen and go back and create that double bond. Okay, so that gives us our second contributing structure. Okay, now notice there's an arrow in between here. This double-headed arrow that's in between these 2 structures is important, because that double-headed arrow in between there says that these are contributors. They're not in equilibrium. They're not one's going to the other, the other's going to. This is what we call the contributing structure. This is the equilibrium arrow, the double-ended arrow. And therefore, that this is the arrow over here says this is the structure that's contributing to our third diagram. So notice, and then we probably could have another arrow going all the way to here that would be contributing to here. But the key here is that a 2-pronged curved arrow shows where electrons are moving. This double arrow shows that we have 2 contributing resonant structures, 2 contributing Lewis dot structures. Okay, so if we're going around and around like this, so we have 3 possible structures for our combination there. Okay, so it's very important we use this curved arrow showing that electrons are moving, okay, because it shows which electrons moved where and which electrons formed that new bond you're forming. So this is very important. We use it all the time in this class. And so organic chemists, you'll see it all the time. So make sure you pay attention to the curved arrow. Okay, so I kept saying the word valid, okay? So what I mean by valid is that we have to follow all the rules for Lewis dot structure. So all of these contributing structures must have the exact same number of valence electrons. You can't add or subtract electrons. That's a reaction, okay? Second, you must obey all the rules for your Lewis dot structure. 2 electrons on hydrogen, 8 electrons on group 2s, and up to 12 electrons on period 3s, okay? The only difference is where the electrons are. You cannot change connectivity. You cannot break single bonds. You can move double bonds, but you cannot break single bonds. And if you have unpaired electrons in your first resonance structure, you must have unpaired electrons in your second structure. So you have to have the same total number of paired or unpaired electrons in a system. So this is just following the same rules for creating a good Lewis dot structure. It's just, it applies to resonance as well. Okay, so what we're going to do is I'm actually going to show you, we've already done carbonate once. I'm going to show this one right here. This is the acetate ion. The acetate ion we're going to use a lot. And so if we were to just draw the structure, it would be C with a carbon and a double bond to oxygen, an oxygen with a negative sign. And then this carbon has 3 hydrogens on it down here. There we go. It's lagging a little bit, but we have to make sure we add our electrons. So we have two lone pairs on the top oxygen, and we have a total of 3 lone pairs on our bottom one. Okay, so we know that the bottom one has a charge, and that -1 charge, because we went back and calculated the formal charge, and we see that we started with 6 electrons, and it has 1 more electron than it started with. So that gave it that negative charge. Okay, so this is our starting place. We now have a good starting point for our resonance structure, but we have 2 oxygens on our system, and they're basically the same. So why can't the double bond be on the oxygen at the bottom? Well, that would be a great contributing resonance structure. So we're going to draw our contributing double arrow down first, and then we're going to move those electrons, okay? So I'm going to change colors too. We're going to take this pair of electrons, move them in to create a double bond there. But now the carbon would have 10 electrons around it. We can't do that. Never going to happen. So we're going to move these electrons up here, and now the negative charge is going to reside on this top oxygen. So when we do that, our contributing resonance structure is going to look like this. O with a negative sign, and then our hydrogens didn't move right here. Okay, so our contributing resonance structure has the exact same charge, the exact same atoms, the exact same connectivity, the exact same number of electrons, the exact same number of pairs. It's just the negative charge is now on a different atom. Okay, so does everybody understand what contributing structures are and why we have to draw resonance structures? Because we can't say it was definitely only on one or only on the other. Okay, so let's continue this and talk about the resonance structure for, actually, I don't want to do this example, but yeah, I don't want to do this example. Go ahead and do this in the book. There's a description of it in the book that I think you'll find interesting. And the reason it has resonance structures is because the formal charges. And so that's where you can actually see that quite a bit. Okay. So let's go back to the shapes of the atomic orbitals. Okay. So when we do the shapes of atomic orbitals, we're looking at the each principal energy level starts out with an s orbital. The s orbital is the simplest orbital and has availability for 2 electrons in it, right? So if we look at the 1s orbital, it's a small sphere, and the next principal energy level above it is the 2. It completely encloses the energy level below it. So the S2 orbital completely covers the S1 orbital. Okay. Now, as we expand out, this will be true for each principal energy level. S orbital will completely cover all of the orbitals from the previous ones. Okay. So in the principal orbital 2, we actually have the availability of our p orbitals. And we have 3 equivalent p orbitals, but they go in different directions. One is going to be aligned with the x-axis, one is going to be aligned with the y-axis, and one is going to be aligned with the z-axis. And the s is going to sit somewhere in between here. So our s is here, and our lobe's there. Now, notice that those electrons are not really touching. This is remember, each of these lobes is the 95% probability of where you could find an electron, not that they're forming these hard shells. So don't forget, this is a cloud of electrons, not a hard shell of electrons. Okay. So this is the second one, and then once we go to the third principal energy level, the first orbital we see is going to be an s, and that third principal orbital is going to completely cover these 2 p's, and those 2 p's don't stick out. That 3s orbital completely covers that whole thing, and they build out from there. Okay, that'll let somebody in. Okay. All right, so where are we going with this? Okay. So with the idea that we have these orbitals, and so that's for each atom has these orbitals. And what we have to do is figure out how we're going to make bonds out of these orbitals. And the way we do that is we overlap the orbital of one atom with an orbital of another atom such that each of these orbitals can share its electron with the neighboring atom. Okay, so orbitals are just with atoms, but when we start sharing electrons, we have to overlap those orbitals a bit. And what we end up with is our 2 nuclei are coming kind of close together, but the electrons are shielding those 2 nuclei, which are positively charged, from each other, keeping them from repelling each other. Okay, so whenever we have a covalent bond, we're always sharing electrons, and we're typically sharing one electron from one orbital and one electron from the neighboring atom's orbital, and we're overlapping those orbitals. Uh-oh. Where'd it go? There it is. Yay. Okay, so if that is true, and that is simply done such that we can do these orbitals, how can we have 4 equal bonds, right? When we have the, the 4 equal things here, we have an s orbital and then 3 p orbitals. We have a p and a p and a p. How are we going to get those to be equal and equivalent? Okay. So what we have to do is, in a principal energy level, we can blend together the same orbitals in that principal energy level. And in this particular case, we're going to take one of the s's, the only s in that principal energy level, and blend it with each of the p's. And we can do it with just 1 p orbital, 2 p orbitals, or all 3 p orbitals. And we call this orbital hybridization. Okay. So when we hybridize orbitals, that means we're going to end up getting things that are, we're going to take 3 different p orbitals and a spherical orbital that would all be pointing in different directions. And because we're blending them together, we're going to get 4 orbitals of equal shape and equal energy. Okay. If we end up with 4 orbitals of equal shape and equal energy, that's how we can get to that tetrahedral configuration that we saw in something like methane. You cannot do it without blending those together, because you'd have one thing in the x-axis, one in the y-axis, one in the z-axis, and then something bonding to your s here in the back. So that wouldn't give you 4 equal spaces. So we must be blending these together and making them all of equal energy to give us this tetrahedral shape. Okay. But I said you don't have to use all 3. You can use just 2 of them. And if we did that, we'd end up with 3, 1 from the s and 2 from the p's, equal orbitals. And they would actually end up being trigonal, planar, because we have 3 equal orbitals in there. But we have 1 p left over. Okay. And when we have 1 p left over, that is going to be above and below the plane of these materials here. Oops, let me redraw that. That does not look pretty. Okay, I'm going to draw it this way. So we have the 3 hybridized orbitals that are going to make this trigonal planar, because we have 3 zones of equal electron density. And then that p orbital is going to be above and below there, because that p orbital isn't shared. Only 2 of the p's and 1 of the s's is shared. And so we get a different shape. We get a different molecular shape. Now, what if we only used 1 of those p orbitals and left with 2 p orbitals that are of equal shape? In that case, that means we're going to have a linear thing, because we have a total of 2 orbitals. So we're going to have a linear structure, and we're going to have 2 p orbitals left. And those p orbitals are going to be on the x and the z axis. Now that gives us an opportunity to overlap in a different way. Okay. Now, if you are overlapping an sp3 hybridized orbital and an sp3 hybridized orbital, that's called direct overlap. Okay. So if we have a hybridized orbital bonding to a hybridized orbital, we have direct overlap, and these are called sigma bonds. Sigma bonds, okay? Because they are directly overlapping each other. Okay. But in the case of this p orbital, it's above and below the plane. And let's say we're going to bring another molecule with that same hybridization up close to it, here and here and here, with another s orbital, another unhybridized p orbital here. You cannot directly get that p orbital to p orbital because the space is already occupied by this hybridized bond in the middle. So we call that a parallel overlap, where it's overlapping above and below the direct overlap bond. And we have a different name for these bonds. We call these bonds pi bonds. So it's pi or pi bonds. Okay, so whenever you see a sigma bond, that's two electrons right in between two atoms' nuclei. Whenever you see a pi bond, that's above and below the bond already made by the sigma bond. So it's above and below that. And so when we need to know how many of these orbitals are hybridized and how many aren't, because it gives rise to different types of bonds and different geometries. Okay, so let's start with just the simple one. Let's take all three and make them all equal. When we make them all equal, we're going to take our P-shaped, our P-shaped orbital and our S-shaped orbital and blend them together. So what's going to happen is the S is going to be blended more toward one side, making it slightly larger. And we end up with a structure that looks kind of like this. So we went from an equally sized orbital on each side in the P to when we blend it together, we get a S. One side gets rounder because of the S. Okay. So what this leads to is now we have a small lobe and a large lobe. And we can squeeze those four hybridized orbitals together enough. And note that there's the little back orbitals are going to be squeezed in between these right here. And these are the big ones. Now, because we have four larger lobes on these things, we have four electronic zones, which gives us the tetrahedral shape. Now, again, they're all equal in size, and that gives us that tetrahedral shape. So if you think about sp3, that gives us our four bonds, four sigma bonds, and a tetrahedral shape. If you want to remember it, it's 1s and 3 p's equals 4 equal bonds. So is it different if we, okay, so let's look at how that applies to carbon, right? Because we know carbon is methane and it has a tetrahedral shape. So we expect it to be there. And when we take each of those orbitals and overlap it with another atom like hydrogen, we end up with a tetrahedral molecule. So if we look at this methane here, so we have our sp3 hybridized orbital on our carbon overlapping with an s orbital on our hydrogen to create a direct bond or a sigma bond, okay? And we have a total of 4 of these and giving us that tetrahedral electronic shape and tetrahedral molecular shape, okay? Let's do the same thing, but with nitrogen. Nitrogen already had 5 electrons, so it only needed to bond 3 times to fill its shell. And so what we end up with is 3 equal bonds to the hydrogen, but we have the lone pair and it takes up space, okay? So notice that this is the exact same shape as the carbon, meaning the nitrogen in this case is also sp3 hybridized, okay? But the orbital that has the lone pair in it still takes up space. So electronically, it's tetrahedral, still has those 4 equal zones of electronic structure. But by molecular structure, because you're only bonding here, you're bonding to the hydrogens only on the bottom, we now have a pyramidal molecular shape. Okay. So, and guess what? Oxygen also has sp3 hybridization, and we see that because if we have them spread out and we show that each of the lone pairs takes up one of these sp3 orbitals, and we overlap directly with hydrogen here to give us our tetrahedral, to give us our sigma bond, electronically, we still have that tetrahedral shape, but molecularly, we only have the 2 bonds going to hydrogen, giving us a bent shape. Okay. So that's why hydrogen is not, that's why water is not a linear molecule like we see here, because the orbitals on the carbon are sp3 hybridized, and that gives them the bent shape we see in water. Okay.
Are those lone pairs, are they pi bonds? Pi?
No, because these are in sp3 hybridized orbitals. sp3 hybridized orbitals only are lone pairs or sigma bonds. You can only have a pi bond with an unhybridized p. Okay, now that's a great lead-in question to, okay, let's only hybridize 2 of those p's. And so we have an unhybridized p and see how that is different, okay? So if we only hybridize 2 of those, we end up with a slightly different shape, right? So we have 1 orbital is s and 2 are p. And so that means that the lobe on the p grows a little bit bigger. It's rounder because we're spreading that s orbital out over 2 p orbitals. So we have a bigger lobe from that. And those are the 3 orbitals that are of equal energy. So they're going to try to spread out and be electronically spread out as much as they can. And when we have 3 equal sites of electronic energy, we end up with this trigonal planar structure where everything's 120 degrees apart. Okay, so that's just 1 of the s's and 2 of the p's. We still have 1 p left. So where does that 1 p go? Well, because these have already, because the hybridized orbitals have already taken up that amount of space to make it flat like this, the p orbital only has a place to go, is to be above and below the plane of that triangle. Okay, so that means that this p orbital is going to be 90 degrees from that trigonal planar orbital. Okay, so we have 3 equal zones and then our unhybridized p. Okay, and notice it is not lopsided. It's the same on the top and the bottom. Okay, so how can we use that? Okay, now only the hybridized orbitals are going to do that direct overlap. That p orbital is not going to do direct overlap. It's going to do the above and below thing. So what does that look like? Okay, so we'll take that same structure and we're going to put 2 carbons close together. And so in this case here, I'm going to start with this. We have 1 of the sp hybridized orbitals is going to bond to hydrogen over here. And then there's going to be another one bonding to hydrogen in the back. And that last sp hybridized orbital is going to bond to another carbon. Each of these is a direct overlap of that hybridized orbital and creates a sigma bond. Okay, but we now have p orbitals. Okay, we have 1 electron in this p orbital and 1 electron in this p orbital. Okay, but we can't go directly there because we have this sigma bond already in place. So that's why we can, all hybridized orbitals create sigma bonds, and the unhybridized p orbitals can be above and below the plane of the above and below the sigma bond that was already created and creates that overlap. So pi bonds are always unhybridized p's, and they're above and below the sigma bond created by the hybridized bonds. So another way to look at this, see this diagram here? We have the hybridized bonds are the ones creating all of the sigma bonds. Right here, all of the sigma bonds are hybridized. The pi bond is an unhybridized p orbital. So we did sp3 where we had 4 equal orbitals. We did sp2 where we had 3 equal hybrid orbitals and 1 unhybridized orbital. Okay, so let's extend that a little bit more and go to, I'm going to skip the slide for just a second, and go to the SP. In the SP, we're going to take one of the S's, the only S, I'm sorry, and one of the P's and blend those together. Now notice the shape gets a little bit different because we have, this is the whole round side here. So it's actually a very exaggerated lobe, okay? And when this bonds directly, it can only bond directly in that hybridized orbital, okay? But what do we do with the rest of them? We have two unhybridized p orbitals. So we have to arrange those such that they're in an X and Y plane that go through that hybridized orbital. So if you look at this right here, we have the hybridized orbital on one axis, one of the unhybridized p's on another axis, and the last unhybridized p on the third axis. That's going to give us an interesting shape when we start bonding that. Okay, so when we get two of these together, what happens? We end up getting the direct overlap with the hybridized orbital. So our direct overlap is the sigma bond between the carbon-hydrogen and the carbon-carbon bond and the carbon-hydrogen bond here. Okay, come on, catch up. There it are. And we're going to get one pi bond from one set of the unhybridized P's. And we're going to get a second pi bond from the other set of unhybridized P's. So what does that look like? Let's blow up this structure here instead. Again, we have our sigma bonds with our hybridized going through the middle here. And we create our first pi bond with two of the P's that are lining up on the same axis. And we create the second pi bond with the two other P's that are aligned on the other axis. So now that generates a linear shaped material. Okay, so do we see how by only sharing one of the p bonds, one of the p orbitals, we're allowed to have two pi bonds. If we're hybridizing two of the p orbitals, we're allowed to have one pi bond. If we're hybridizing all three p orbitals, we do not have any pi bonds. Okay, but in these examples, it's only been carbon and hydrogen. Is that true? Well, no. This works for any atom that is sp3 or sp2 hybridized. So let's move to a different compound. Let's move to this one right here. In this case, we have a carbon, and because it has three things bonded to it, we're pretty sure that that is an sp2 hybridized carbon. Okay. Now, this oxygen right here also turns out to be sp2 hybridized. One for the sigma bond created in between the two, and one for each of the lone pairs, meaning it also has an available p orbital. So whenever we see a double bond between an oxygen and carbon, that double bond is created from a p orbital on the carbon, no, it auto-corrected there, and a p orbital on the oxygen that are overlapping to give us our pi bond. So the hybridized orbitals gives us the sigma, the unhybridized orbitals give us the p's. And it's not just carbon, it's anything that is sp2 hybridizable. And like I said before, carbon, nitrogen, and oxygen all can have hybridized orbitals. All right, questions on that? So think of hybridized orbitals as sigmas, unhybridized p's as pi bonds.
So if it's electron geometry is trigonoplanar, it's a sp2.
Yes.
And then if it's electron geometry is a tetrahedral, it's a sp3.
Correct. And
By default. And then
If
It's
it-
hybridized because I forget why, but it has those.
it saves energy to have them all be equal in energy. So that's why we hybridize. But I wanted to get you to say that the sp, because it has 2 electronic zones, is linear. So 4 electronic zones tetrahedral, sp3. 3 electronic zones trigonal planar, sp2. 2 electronic zones linear, sp. Okay.
So by default, each of those, if you know it's electron geometry, you can kind of determine like how many p's, excess p's it has.
If you draw the Lewis dot structure correctly, yes, I agree with that. Okay. All right. There we go. Okay, so to summarize that, what we're going to see is almost anything that is bonded to 4 things or has a number of bonds and a total of those 4 electronic zones, like lone pairs, are going to be sp3 hybridized. And they are going to try to be close to that 109 degrees if they're all approximately the same size. And sp3s will only have sigma bonds. Okay. Once you have 3 things bonded to carbonate, you know that you had to have a hybridization where you only have 2 of the p's. So that means you have an available p orbital for pi bonding. And because we have the 3 equal, we now have that trigonal planar geometry. So think a carbon with a double bond. Okay. And when we go to those 2 groups bonded, we have 2 p's available. Those 2 p's end up giving us 2 pi bonds, or in this case, a triple bond. So we have 1 sigma and 2 p's, 2 pi's, to create a triple bond between those 2 carbons. The other sigma bond is the one to the outside. So 1 sigma bond here, 1 sigma bond here, and then 2 pi bonds. All right, is that starting to make sense? Okay. Okay, so hybridization is done because it saves energy, and if we didn't hybridize, our molecules would not be the geometry we find them. So knowing that the geometry of the molecules is this way is proof that we have this hybridization of orbitals, or at least strongly suggests it. All right, questions on hybridization and the shapes of these single, double, and triple bonds. Okay, now we're going to take everything we've just learned about bonds that are polar, molecules that are polar, shapes of these electronic structures, and start looking at combining different atoms together to get different things. Okay, so when we combine different atoms of different groups of atoms together, we end up with, they can have different physical and chemical properties. And so when we have something that is something we can do reactions on or do chemistry on, we call it a functional group. And it can be an atom or group of atoms that shows a specific physical or chemical property. For example, if it has a polar bond, it'll react. So that's a functional group. If it has a double bond, it'll react with certain things. So that's the functional group. Okay. So functional groups are important for 3 reasons. 1, we can use it to help us divide up the different organic compounds into different classes. And that helps us organize our system and look for similarities in reactivity. Second, it gives us the places at which the chemical reactions will happen. For example, if you have a carbon-oxygen double bond, certain chemicals will react with that, but certain chemicals won't. So those sites are very important. And then the other cool thing it does is it helps us name them. The most important functional groups are named Morse, and therefore we get to know how to name our chemical structures. And naming our chemical structures is really important because we want to name it so that if I draw it, And if you draw it and we both have the same number, I mean, we both use the same word, we're going to come up with the exact same compound. There's no ambiguity in our naming system. Okay, so let's go over a few functional groups because we're going to start throwing these out quite a bit. In fact, when I was talking about some physical properties, I thought maybe that we talked about some of these, but the first functional group we want to walk to is alcohols, okay? Now, an alcohol is an organic compound that has an OH group on the end, okay? So it can be any chain of carbons on there, and there can be other functional groups on there. But when we have just an OH group on the end of a carbon chain here, that group is called an alcohol, okay? And its reactivity comes from the fact that this hydrogen and this oxygen are way out here at the end, and we will see different reactivities on how we use that. And it bonds in different ways. Okay. The next functional group I want to talk about is the amine. Okay. So instead of having an oxygen hydrogen here, in this case, what we're looking at is things with a carbon nitrogen bond. Okay. However, because nitrogen can bond 3 times, we can actually have 1 carbon nitrogen bond, 2 carbon nitrogen bonds, or 3 carbon nitrogen bonds. And so they have different classifications, okay? So if we only have 1 carbon nitrogen bond, and it's assumed the other 2 bonds are to hydrogen, we end up with what we call a primary amine. Primary amine. Come on, there you go. Because you only have 1 carbon on there, okay? So if you have 2 carbons attached to your nitrogen, like the one here in the middle, we call that a secondary amine. And then if we extend that so all of the available bonding sites for that nitrogen are used, we call that a tertiary amine. Okay. So primary amine is 1 carbon, secondary amine is 2 carbons, tertiary amine is 3 carbons. So, and these have different functionalities than alcohols, and because we have a nitrogen instead of an oxygen. Okay. The next group is a whole group of different things, and they all involve the carbonyl group. The carbonyl group is a C double bond O. Okay. Now, to draw an analogy to what we just talked about, the carbon is sp2 hybridized. The oxygen is sp2 hybridized right here. That means we have a pi bond between that carbon and oxygen. And this gives it some really cool functionality because depending on what you hook to that C double bond O, it tells you a bunch of different types of functional groups. So the carbonyl group here actually has multiple functional groups associated with it. So if you have a hydrogen attached to the carbonyl, either 1 or more, it's called an aldehyde. Aldehyde. Okay. So we have a carbonyl. If there's a hydrogen directly attached to a carbonyl, it's called an aldehyde. Okay. And it can either have a hydrogen or a carbon on the other side here, but it has to have at least 1 hydrogen on that carbonyl. Now, if we take that hydrogen away and put 2 carbon bonds to that carbonyl, it's now a different functional group because that hydrogen is more reactive than the carbon, and therefore we call this a ketone. Okay. So 1 carbon or 1 hydrogen on a carbonyl, aldehyde, 2 carbons on a carbonyl, ketone. Okay. But are we restricted to just bonding hydrogens and carbons to that carbonyl? Well, of course not, because we have a lot of different things we can do. So if we, instead of being bonded to a carbon or a hydrogen, we put an OH group on there, remember that from alcohol, we actually have a new compound now. We have a carbonyl with an OH group on it, and that's called a carboxylic acid, or the carboxyl group. So an example is acetic acid or vinegar. This changes its reactivity even more. Each time we change that substitution on that carbonyl group, we change how it reacts and what it will react with. So it's important to keep those functional groups learn those functional groups, and we'll use them throughout the rest of the semester. And those are the functional groups we'll be talking about in individual chapters as we go forward. Questions on hybridization or functional groups? I have a raised hand.
So you said if the carbonyl on this slide, if the carbonyl is attached to one hydrogen, it's an aldehyde?
Correct. At least one hydrogen.
Okay. And then,
Because there is the simplest one where we have two hydrogens on it, and that is still an aldehyde. That's called formaldehyde. But if there's a hydrogen on it, it's an aldehyde. If there's only carbons on it, it's a ketone.
oh, I thought it was more than one. It's a ketone.
It has to have two carbons on it to be a ketone.
Thank you.
Yeah, because that carbon, because it's already double bonded to oxygen, it can only bond twice. So I guess technically that either one is true, but it's two carbons or only carbons. Because it's all, the carbonyl can only bond to two other things after it's, because it's already bonded to the oxygen twice. Okay. All right, any other questions? Right here. Okay, we have a little bit of time, so I'm going to go ahead and move into chapter 2. And again, these are posted on the track site as well as Canvas. Okay. So the next thing I want to talk about is acids and bases. So the first thing we think about when we think about organic chemistry is how things bond. And why does carbon bond 4 times? Well, we've learned that. We've learned that it's orbitals and it's hybrid orbitals that allow us to do that. But what are some other driving forces in reactivity that we have in organic chemistry? And the next most important thing is the acid and base reaction. Okay. So traditionally, what we learned in Gen Chem is that an acid is some substance where a proton protonates water and you create a hydronium ion. If you create a hydronium ion, that means you have an acid. Okay. Now, he also said that in contrast, by deprotonating water, taking a proton away from water and giving us a negative ion, makes hydroxide ion. That is by definition a base. Okay. So that means you must have water and you must transfer a proton. Okay. So that being said, that is a classical definition. However, in organic chemistry, we don't use water all the time. In fact, a lot of the times we want to exclude water from our system. So we need a slightly different answer. So in the classical sense, we have things like our water is going to react with a compound of hydrogen chloride. When you dissolve, come on, what about laggy doing? When you dissolve hydrogen chloride, which is a gas at room temperature, into water, it dissociates to give you this hydronium ion and the chloride counter ion. Come on, come on. There we go. So it gives us the hydronium ion and the chloride ion. Okay. So that's okay. And we have, once it dissolves, it forms these two things, hopefully in a sea of extra water. Okay. In the case of bases, we typically have some counter ion associated with it, like sodium or magnesium or potassium. Occasionally, we can actually do it with a non-metallic system, and that's in the case of ammonia. In the case of ammonia, ammonia will take a hydrogen away from here, generating a cation, liberating the hydroxide ion. So the bases are much more, are where we have the hydroxide counterbalanced by some positive charge. Okay, so why do these work? Okay. Well, we have to go back to our Lewis dot structure and that concept of moving electrons with our curved arrow. How does that work from space to space? And so if we start out with that ammonia by itself, it's a neutral molecule and it has a lone pair on nitrogen. We have water, which is a neutral molecule and has 2 lone pairs on oxygen and has that hydrogen there. Okay, so we have 2 neutral molecules and we're converting it into 2 charged species. Okay, so we have to be able to transfer, in this case, a hydrogen from one compound to the other. So in doing that, we're going to use the lone pair from the nitrogen here to create a new sigma bond with the hydrogen on water. Okay. When we create that new sigma bond on hydrogen with water, that means it no longer needs the electrons here and it gets shared. And the shared electrons in the sigma bond here, and it goes and sits on the oxygen. When it does this, we had 2 electrons here counterbalancing ourselves. And when we shared one of those electrons with this hydrogen to form that sigma bond, we now have a formal charge of +1. So the net charge on our new sigma bonded molecule here is +1. Now, we had shared electrons, but in this sigma bond here, but now they're residing on the oxygen. It has 1 more electron, and therefore it is a formally charged species there. Okay, so we're using that curved arrow technique to make sure we know exactly where the electrons are flowing. And in this case, we've actually moved an atom, right? We move the hydrogen from one compound to the next. Okay, that's going to be important in our next definition of acids and bases. Okay, so in our next definition of acids and bases, this is the Bronsted-Lowry definition. And in this case, you don't have to have water, but you do have to transfer a proton. Okay, so in the case of an acid, you are going to donate a proton. You have a proton that you're going to give away. Now, by proton, I mean hydrogen, then it's not going to take its electrons with it. So that's what I mean by proton. It's not really a proton floating around in space. It's just, the electrons are not, it's not taking the electrons with it. That means that in contrast, the base must be the one that's willing to accept that proton with the electrons it already has. Okay, so that brings about an interesting thing. So when an acid reacts with a base, we now have the acid now can accept a proton. So when an acid reacts with a base, it becomes a conjugate base because it's transferred its proton, but now that it's transferred its proton, it can now accept a proton. And so we have this interesting pair of things. An acid will become a conjugate base. Our base, once it's accepted that proton, can now become a conjugate acid because it has an extra proton that it didn't have before. Okay, so that being, what does that look like? I mean, what that seems crazy, right? Well, let's look at that hydrogen chloride that was in a gas, and we're going to dissolve it in water and see what happens there. Okay, so this is by definition our acid because it has the proton it's willing to share. Okay, now if this is the acid, that makes the water the base. Okay, so when the acid transfers the proton to the water, right here, we now have the hydronium ion, and it has a positive charge. What happened over here? Well, the chloride lost a proton but kept its electrons and got to be a negatively charged chloride ion. Okay, so this chlorine right here of the hydrogen chloride has changed from being the acid structure to now being willing to accept a hydrogen. That makes it the conjugate base. Okay, because now it can go back and accept a proton to become an acid again. Okay, the water that was our base now has a proton willing to that it can share, and now that makes it its conjugate acid. Okay, so a base becomes a conjugate acid, and that's our conjugate acid base pair. The acid becomes the conjugate base, and that's our pair. Notice that this doesn't the water doesn't become hydrogen chloride, and the hydrogen chloride doesn't become water. We have to follow where the proton left from, and that becomes our new conjugate system. So notice the hydrogen was transferred off here, leaving the chlorine for our conjugate base. The hydrogen was added here, so that's where we're following our conjugate acid. So in this case, we're following the proton. All right. And we're right, well, no, I can do one more slide. Okay. So unlike the Arrhenius definition, you do not have to have water in a Lewis acid base. Because remember, the requirement was a proton available to transfer was an acid, and a willing to accept a proton was a base. So we can use organic materials that are not water to do this same functionality. So let's take a compound right here. We'll call this acetic acid. It's one of the carboxylic acids we talked about in the last chapter. And another compound, neutral organic compound, ammonia. In this case, because it has acid in the name, we think it's going to be the acid, and this proton is going to transfer to the ammonia. When it does, it now has a negative charge. What else had a negative charge? Hydroxide had a negative charge, and it was called a base. Okay, so if you lose a proton, you become a conjugate base because of that negative charge. Okay, so our acid has become our conjugate base. But what happened to our ammonia? Our ammonia was acting as a base, which means it had to accept the proton. So when it comes over and accepts the proton, it now has a positive charge. And to get back to neutral, it can now donate that proton. So it's now the conjugate acid. Okay, so we can do this exact same proton transfer and create conjugate acid base pairs in the absence of water. Okay. So why does it work? It again works because the electrons from the base are going to create a new sigma bond with the hydrogen of the acid. And the sigma bond that was bonding the proton to the acid are going to go and reside on some atom in that molecule, generating a negative charge. Okay. So in this case, the proton is the hydrogen that is going to create a new sigma bond with the base. The acid is the one that's going to break a sigma bond with that hydrogen to generate the ion. Okay. So are we really transferring a hydrogen, or are we moving electrons around here? So that's kind of looks like what's happening here, that we are using electrons to reach out and create a new sigma bond. And we're taking the electrons from an old sigma bond and putting them onto the non-hydrogen portion of our molecule. Okay. Yes, there's a question.
Do you have to transfer the pair of electrons from the nitrogen to the hydrogen first before you can transfer?
It happens all at once. It's a bond forming and bond breaking reaction.
Okay.
And because you can't just have the hydrogen with, you can't just lose all the electrons around your hydrogen and have it wander around as a proton. That would be way too reactive. So the electrons from the nitrogen have to reach out, start forming the bond with the hydrogen, and then While that bond's forming, the bond with the oxygen starts to break. Okay, and we'll do a little more about mechanisms later. Okay, so what I'd like to do is I'd like to stop here because it's right at 12:20. So I think that's right at our stopping place. And we'll continue on with these Bronsted-Lowry acids and base and talk about acids and base pairs and the driving force. You'll know which way the reaction goes based on that conjugate acid, that acid pair, conjugate acid base pairs. You can see which direction it goes by comparing the strengths of those. Okay, I'm going to go ahead and stop sharing and stop recording. And if you have a question, go ahead and stay behind.
Thank you, Professor.
Thank you.
Thank you.